So now we're going to look at the idea of the mean of a random variable. So if our random variable is called x and its PDF is denoted with an f, then the mean, which is denoted by mu, the Greek m, the mean is going to be the integral of x times f of x. And so the mean is also called the average value. It's also called the expected value, especially when you're doing probability. It's not the same thing as the median or the mode. Those are different notions of centrality. We won't actually really be talking about those. And you know what else? I've been kind of sweeping something under the rug, and that is that there's different kinds of random variables. And most of the time, we're not going to talk about this, but actually, I should be saying a continuous random variable. Only continuous random variables actually have probability density functions. It's also possible to talk about discrete random variables. So for instance, like what happens when you throw a die or flip a coin, right? And that there's only a finite number of outcomes. It's the same basic thing, but things are written in terms of sums instead of integrals, and it's actually a lot simpler. But what the heck, we're in a calculus class, so we're not going to talk about simple stuff. But except for this particular example, which I just wanted to bring up because it sort of makes my point, and it's a handy calculation to do if you've never done it. So if we look at the lottery, so some lotto game, let's talk about the expected value of playing that game. What is the expected value of the game? Well, the reason why we have x times fx is because you want to think of it as the value of the outcome, x, times the relative probability of that outcome of occurring, f of x. So for playing the lottery, let's think of it as the value of the game as being the profit, for x being the number which happens to be the winning number, times the probability that the ticket that you have has the winning number. And then the only other outcome is that you lose. And so then we'll look at the profit that you get if you lose times the probability that you lose. Okay, so this is a discrete version of this one that I've written down below. It's like x, possibility x1 times probability of x1 occurring plus possibility x2, the value of possibility x2 times the probability that x2 occurs. And you could think, oh, if I added up like a whole bunch of those and then took an integral, it would look like this kind of thing. But anyways, so if we just throw in some random numbers in here and say, okay, so profit. Suppose that the payoff for the lottery is $10 million. Okay, so then the profit is going to be $10 million minus the $2 that it cost you to buy the lottery ticket. And then we multiply this by the probability, and say there's like 60 million people playing the game, so your chances are 1 out of 60 million. I made these numbers up completely, well, not to make a pun, but at random. If you want to do it for a particular lottery game, I'll leave it up to you to adjust the numbers. So the profit, if you lose, well, you're out $2 for the ticket. And then what's the probability that you lose? Well, it's the complementary probability. So 60 million minus 1 out of 60 million. Okay. And so punching in these numbers, we get something like 0.1666666. And then we have minus, by the way, that's clear, but this is negative because that's the cost of the ticket. So it's negative profits because you had to pay for it, right? Minus 1.99, a whole bunch of nines. And then that ends up being negative $1.83 and whatever change. So on any given play of the game, you're not going to actually lose $1.83, but you should expect that over repeated plays of the game, your profits are going to be about minus 1.83 times the number of times you played the game. So if you play the lottery 1,000 times, you should expect to lose $1,830 something, basically. This is why the lottery is a tax on people that are bad at math. All right. So this is the notion of mean. So for X and Y with a joint PDF F, the X mean, or the X component of the mean, is going to be mu1, which is the integral over everything of X times F of XY integrated, integrated in whichever order you want. And if we look at the y component of the mean, it's just going to be the symmetric other thing. So we'll call it mu2. Again, it's the integral over everything, and this time it's y times f of xy. Okay, and then the mean of the joint distribution is going to be the point with coordinates mu1, mu2. So that's some point in R2, right? And we won't do too much at the moment in terms of physical interpretation, but exactly the same thing happens in the physical interpretation when f is a density function for mass. And then in that case, this exact formula gives you center of mass. We're not going to talk about it so much right now because that's really the center of mass is a thing you do with three-dimensional objects, much more than two-dimensional objects. So we'll come back to that when we do triple integrals.